Okay, so today we are going to talk about enzymes. And primarily we will be talking about thermodynamics and how these thermodynamics influences the mechanisms of enzymes. Now, to start out, let's make a very brief, easy definition of life. We're talking about substrates becoming products. Now recall that this reaction is reversible, and because it's reversible, it can go either way, and we can determine an equilibrium constant for this reaction. Now, if we consider a spontaneous reaction, and we measure the delta G, which is the free energy change of a reaction, we can measure the energy of the substrate, and then this substrate will convert to a product, and the free energy of the product can be measured also. So this difference between substrate and product is the free energy change of the reaction. Now notice, because it's a spontaneous reaction, the substrate immediately converted into product, so this is going to be essentially a negative delta G, because we are losing free energy, and that gives it a negative delta G and a spontaneous reaction. Now, every reaction has its own inherent delta G measurement, a change in free energy. And this can be measured as the standard free energy change. And the standard free energy change is delta G 0. And delta G 0 is going to equal negative RT. R equals the gas constant. T equals temperature in Kelvin. And then the final term in here is going to be the natural log of the equilibrium constant. So this is the calculation for the free energy change of any reaction, allowing the reaction to reach equilibrium. Now let's take a look at this reaction with the situation of a spontaneous reaction, where the forward reaction is moving very rapidly. That means that our product concentration is going to be much, much greater than our substrate concentration in a spontaneous reaction, because the substrate is converting into product very rapidly. That will give us a very large number for KEQ, the equilibrium constant, and when we take the natural log of a large whole number, that will be positive. Multiply that by RT, and we have the negative delta G, indicating that this is a spontaneous reaction. Now, this is the standard free energy change, the delta G 0. But in biochemistry, we have another consideration to make, and that is the delta G 0 prime. And the delta G 0 prime in biochemistry is essentially the same equation that we see in chemistry, except that we now need to include the reaction occurring at pH 7. Now, considering the standard free energy change for a biochemical reaction, we have our equation of the standard free energy change equals negative RT in the log of the equilibrium constant. This is a very useful term because this is the inherent free energy change of any chemical reaction that we can measure. Now, in biochemistry, the problem is that biochemistry is very dynamic. And what that means is that we will seldom reach equilibrium in any reaction. So that means that the substrates and products are changing over time because of different inputs and regulatory elements. So in order to consider this, we need to determine what the free energy change is at any particular point in a reaction. And this is important because the substrate and products of our biochemical reactions are changing at all times. So in order to measure this, this is the free energy change at any point during the reaction while it's taking place. And this term needs to, of course, include the standard free energy change for the reaction because that's the inherent property of the reaction. And now we are going to add a term that will take into consideration the concentration of substrate and product at any given time during the reaction as it's trying its best to achieve equilibrium. And that's this term plus RT log of Q. Q is the reaction quotient. The reaction quotient is similar to the equilibrium constant in that it is equal to the concentration of product over substrate, but this is not necessarily at equilibrium. This is the concentration of product over substrate at any point during the reaction sequence. So what this essentially means is that if we know the product or substrate concentration at any time during the reaction, we can calculate the delta G and determine if the reaction is going to move forward or backwards. So what does that mean? If we have a very large amount of substrate at one point in a reaction, that means that our Q, our reaction quotient, is going to be less than 1. The log of less than 1 will equal a negative number. When we take this negative number, put it into our free energy calculation term here, we see that the delta G equals a negative number, which means that under high concentrations of substrate, the reaction will be moving toward product. Now let's take the opposite example. If we have a high concentration of product, this will mean that our reaction quotient is greater than 1. Log of a number greater than 1 equals positive. And therefore, we take the positive number, place it into our free energy equation, and our delta G is going to be positive, indicating that the reaction is going to want to move in the opposite direction. So this is the most useful term to us in biochemistry, and we are going to be coming back to this term of free energy calculation at any point in a reaction very, very frequently, because in biochemistry we have situations where substrate can form product if the product is part of a sequential reaction and this reaction is inhibited, the product will build up. If this product builds up, then there is a potential to shift this reaction backwards. And therefore, we can calculate the free energy change based on the substrate to product relationship. Now likewise, if we have substrate to product 1, and if we have this reaction going to product 2 in the next step of the reaction, what happens if we have this step accelerate? That will mean this reaction will increase greatly, which will decrease P1. Decreasing P1 is going to essentially prevent the reverse reaction, because this will drive this reaction to ensure a negative delta G. So this equation needs to be studied, and the relationship between substrate and product needs to be incorporated and studied in this reaction, because this will become a very large factor as we look at metabolic pathways and their regulation and control. Okay, another important feature to remember about free energy changes in biochemical reactions is that the reactions themselves are additive. So what does that exactly mean? Well, let's take, for example, a reaction of glucose plus inorganic phosphate is going to form the product glucose 6-phosphate. Now this reaction is a key reaction in biochemistry. This is the first step reaction in glycolysis, and it's mediated by an enzyme called hexokinase. We'll be reviewing this enzyme quite a bit. Now, if we were to measure the standard free energy change of this reaction, delta G 0 prime, this free energy change equals 13.8 kilojoules per mole. Now, the important part of this number to notice is that this number is positive. So a positive standard free energy change indicates that this is an unfavorable reaction. Now, being an unfavorable reaction, it requires endothermic energy. We need energy input into this reaction to make this happen, because attaching inorganic phosphate to glucose is not a favorable reaction. But we know this reaction goes very efficiently in biochemistry because it is the first reaction in glycolysis. And glycolysis is the pathway to produce energy. So, how do we make this reaction go forward? Well, we are going to couple this reaction with another reaction. And that reaction is the hydrolysis of a phosphate linkage on ATP, adenosine triphosphate, to form adenosine diphosphate plus inorganic phosphate. Now the delta G 0 prime of this reaction is negative 30.5 kilojoules per mole. Important feature here to notice, this is a large negative free energy change, which means this is a very favorable reaction. So this is the consideration of a coupled reactions. So in order to make an unfavorable reaction go, we need energy to put into this reaction, so that energy we are going to harness with the use of another reaction that is favorable. Now this will give us, essentially, if we add these reactions together, we will see that this gives us a coupled reaction. Now, the standard free energy change of this reaction is 13.8 kilojoules per mole plus 30.5 kilojoules per mole for the second reaction. This equals negative 16.7 kilojoules per mole, which is an exergonic reaction. So this reaction will proceed forward. This is the term that these reactions are additive. This is a feature that we will see in many biochemical reactions when reactions are unfavorable in the forward direction and they need a little bit of help with the negative free energy change of a separate coupled reaction. In this case, we are using the hydrolysis of a phosphate linkage on ATP, which is a high energy bond, to release the phosphate, which is now going to be used to generate glucose 6-phosphate.